Hi to everyone. The work that I'm going to present is preliminary result from a collaboration between Norwegian University of Science and Technology, SINTEF Industry and CERN, the European Organization for Nuclear Research. The title is Flexible Graphite as Beam Damping Material in the TDE blocks of LHC, the Large Hadron Collider. The Large Hadron Collider is a particle accelerator which is built in Geneva in Switzerland, and it's a long circular tunnel of 27 kilometers built to 75 up to 175 meters underground. On this tunnel there are two counter-rotating particle beams that collide and deliver a high amount of energy and can reproduce conditions similar to those conditions present right after the Big Bang explosion. So the particles are hadrons, and one type of hadrons are protons. The goal is to explore the boundaries of the so-called standard model, and one of the most recent and most famous observations is the Higgs boson on 2012. As concerned the future development, the Large Hadron Collider is going to be updated, and its power is going to be enhanced. It will be called High Luminosity LHC, and it will be capable of accelerating protons at an energy of 14 teravolts. At a certain point in the circular path, the beams are extracted in a tangential trajectory and finally damped by two identical cores. These cores are made of several blocks of graphite with different densities, and the main focus of this project is especially on this part here, which is made of flexible graphite sheets. This core is made of 1,700 sheets of flexible graphite, each one with 2 millimeters of thickness and 1 gram per cubic centimeters of density. So the total length is more than 3 meters, and the diameter is roughly 62 centimeters. So the sheets hold the contact together with weak contact forces. And what happens when a beam impact on a solid target is that it can originate a thermal shock due to the collision between the particles, that is, the protons and the nuclei of the solid materials. So this collision occurs in a very short time called the deposition time, and a large amount of energy is delivered from the particles to the material, and it is transformed on heating very suddenly and in quasi-instantaneous heating conditions, and with these values of density one can expect a temperature that can overcome 2000 Celsius degrees. Due to this thermal shock, the material can also experience very high pressure due to the surrounding material mass inertia that prevents the thermal expansion. So the main goal of this project, this collaboration, is to understand the material behavior when it undergoes very high pressure, and also the coupled behavior between thermal and mechanical response of the material. And second is to build a constitutive model which should be suitable in our range of deposited energy, and also to be implemented in a finite element model, also taking into account the amount of energy in the future upgrade of high luminosity Large Hadron Collider. Usually this material is not used in structural application. It's used mostly on sealing and thermal or electrical application. Commercially, there is a wide range of density available, and what should be pointed out is that its flexibility is given by pure mechanical interlocking, so there are several deformation units that are interlocked among themselves and make the material porous, and it can be also considered like a compacted granular material. It is orthotropic in with respect to several thermophysical properties, so electrical conductivities, thermal conductivities, and thermal expansion, for example. And in order to understand and to have a global look at the material from a macroscopic point of view, uh, we set up a static tensile tests in the in-plane direction. The material chosen is Sigraflex from SGL carbon, and here in the picture it is shown as delivered, so it is in the shape of very thin foils, 2 millimeters of thickness, and its tensile strength is very low. It can overcome 4 megapascals, and also the elongation at break can overcome 1% of value. Due to the low strength, special care has been given to the specimen's preparation. So the specimens were cut by means of a water jet cutter machine at NTNU lab, and here's the geometry of the specimen, which is very small with a cross section of 16 square millimeters. The specimens were tested in a uniaxial MTS universal testing machine, and 8 specimens were tested. Each couple were tested at different strain rate from 0.01 millimeter per second up to 10 millimeter per second. From the first test, it was noticed that the fracture location was hard to capture with only one DIC camera, because the fracture could occur at the front surface and it was not visible in the opposite surface. So it was decided to use two-side DIC in order to register both the front edge and the side edge, and to be sure to capture the first fracture location. Here it's possible to look at the test results. So in this picture one can see the stress strain static curves. The strain used was measured both from the front view and side view, and 2 different gauge lengths were used. One gauge length is the nominal gauge length of 32 millimeters, and the second is a short gauge length close to the fracture location. It should be noticed that the sampling frequency for high strain rate test was not sufficient for good precision of the results. The behavior is quite brittle, and in all the strain domain the curve is non-linear, and there is no evident shift between an elastic and a plastic region. For all the tests, the strength was well scattered around 5 megapascals, and the strain at break was always lower than 1%. About the strain rate effects, there was no strain rate effects neither on the strength, so on the maximum stress, nor on the strain at maximum stress. It was calculated also the Young's modulus from the low strain rate testing, so from 0.01 and 0.1 millimeter per second test, and the values calculated was in accordance with values from literature. Also, a short discussion can be made about the deformation mechanism. First, it should be recalled how the material is made. It is made of compressed particles which initially have worm-like shapes. These particles, after compression, are also called deformation units, and the microstructure can be seen as two scales microstructures. First, the larger scale is represented by the relationship among each worm, so the friction forces that occurs at the boundaries of each compressed worms. But then there is a smaller scale that is related to the behavior of microsheets, which constitute basically the skeleton of each worms. These microsheets are several basal planes stacked together, and they are wrinkled due to the porosity due to the initial porosity of each worm-like shape particles. So Dowell and Howard hypothesized a contribution to the deformation by both the unwrinkling of microsheets and unwrinkling of deformation units. So the first contribution is more similar to the deformation mechanism of polycrystalline graphite and pyrolytic graphite. So by means of dislocations and shear among basal planes, this can also be confirmed by a simple fitting. And here in the plot in the left, one can observe that the fitting has been taken with a power low, which is typical of polycrystalline graphite, and it's very good up to 3 megapascals. And here probably the contribution to deformation is given by the unwrinkling of microsheets. But above these values, maybe the component of the worms, of the sliding of worms boundaries is more important, and then the behavior tends to deviate from before. So we have a high forces region. So as a summary, we can say that the test procedures for Single-Flex for flexible graphite is must be carefully tuned because of the low strength of this material, especially in the in-plane directions, and it's also hard to capture the first location of the fracture. And about the stress strain curve, it is nonlinear in all the strain domain, and it has brittle behavior, but not apparent rate effect is visible on the side strand and strain at break up to 10 millimeters per second. As a starting point for future modeling, it is important to notice that some analogies would be possible with other form of graphite, such as polycrystalline and pyrolytic graphite. Thanks for your attention, and I'm here if you have any questions. I'm here to answer.